Namaskar and welcome back to the course on statistical physics of phases and phase transitions. We have been studying the Ising model and we'll continue to do so in this lecture as well. So a quick review of what we have done so far. If you look at the Ising model on the square lattice, we provided an argument to show that there is a broken symmetry ferromagnetic phase at very low temperatures. Okay. So if you look at the phase diagram based on our arguments, you will see that there is a phase at low temperatures and the magnetization is fully developed. And then if you go to very high temperatures, you get a paramagnetic phase. And the idea of the survival of ferromagnetism in two dimensions comes from the fact that you have these domain excitations where domains of downspins are thermally excited, but their excitation probability is very low because the energy of such domains, their cost is proportional to the length of the domain wall. And this allows the system to hold on to ferromagnetism even at small finite temperatures. We then went on to do a very interesting analysis of Kramers and Monnier, who had shown that the Ising model has a duality to another Ising model with a different coupling constant, and that the relationship between the two coupling constants, K star and K, are given by this relation. Now, based on some very general arguments, we then went on to argue that there has to be a phase transition in the Ising model at some temperature. And using the duality, we concluded that the temperature is something like some 2.25 times the exchange constant. So this is how far we have reached in our study of the Ising model. We are pretty confident that there is a low temperature broken symmetry phase, a paramagnetic phase, and there is a phase transition. Okay. What we are going to do in this lecture and the following lecture is we are going to study the Ising model using a technique called as series expansions. So I will broadly discuss the idea of series expansion, and in this lecture we will study the low temperature series expansion. And in the following lecture we'll look at the high temperature expansion. And we will sort of realize that there is some connection between these expansions and duality, and we'll be able to make some interesting physical insights into duality. Okay. So when we say series expansions, which we have roughly seen when we discussed the interacting particles model, we had an expansion in a small parameter. So I'll just go through the general ideas of when we can apply series expansions. So most of the models that we have studied, they have a few dimensionless coupling constants, and very often we will be able to solve the problem exactly in some regime of these coupling constants. So we'll be able to find a regime of coupling constants where you have an exact solution for these models. If you look at the square lattice Ising model, we can solve the problem exactly in two limits. If I take the coupling constant K to be the exchange constant by temperature, then K equal to infinity is the zero temperature, and there we have solved the problem exactly and found that the ferromagnetic state using the symmetry breaking field, etc., will produce a unique ground state which has broken symmetry. And we can also solve the problem exactly in the K equal to 0 limit, which is, you can think of it as either J is the exchange constant being 0 or temperature being infinite. What this means is that you have essentially isolated spins. Each site is just independent by itself. It's not interacting with any other site, and that's sort of a trivial exact limit. So both these limits we can solve exactly. So the idea of series expansion is to start from one of these states and try to find a small parameter that will sort of control our calculation of the partition function. So we'll try to expand the partition function in powers of this small parameter and try to see how well we can try to capture at least the physics just away from these exact solution points. So this is the idea of series expansions in general. So series expansions were very popular in the early studies of statistical mechanics. A lot was learnt about variety of different systems using these methods. Let's see how this works in the case of the Ising model on a square lattice at low temperatures. So let's set the language out first. So I have a square lattice with n sides, and there are L tilde square number of sides, and they are labeled by capital I, and as usual a spin configuration is described by the Ising variables at each site, and this is a configuration with a set of all spin values at different sites. The Hamiltonian is the usual Ising Hamiltonian with this ferromagnetic Ising interaction between nearest neighbors. And for the sake of illustration, I am also going to add a magnetic field. This is not essential for our discussion, but it will be useful to extract some physics. So I am just going to keep this. So the temperature is T and the coupling constant therefore is J by T. Okay. And the magnetic field that we have applied, in our units, the magnetic field have dimensions of energy, and the coupling constant by which it enters the problem is this H tilde, which is H by T. At zero temperature, we have seen this several times now, the state is the fully polarized state, and I have prepared the state this way by applying a symmetry breaking field, etc. So if I look at the ground state energy, the ground state energy is just each bond, each link has energy negative J, and there are two n links. So the energy associated with the interaction term is minus 2 times nj, and each spin is pointing in the direction of the magnetic field. H is considered positive here, so the spin is considered in the direction of the magnetic field, so it gains an energy of H, and that's why you have this ground state energy. Now what I am going to do, just for the sake of ease of calculation, I am going to take the energy of any configuration relative to the ground state. So I am going to define E of configuration is the Hamiltonian value minus E0. So this is sort of, if you wish, the excitation energy of the configuration C. And I will write the partition function this way, where I sum over all the configuration e to the minus EC by T instead of the H that we usually put. And I should remember that when I do this, when I put back the free, when I want to compute the free energy or any quantity, I have to just put back this E naught. So the free energy would then be E naught minus T log Z. Okay. So this is a simple bookkeeping device. Okay. So now we have to identify a small parameter. So obviously the small parameter cannot be K, because K is blowing up as T goes to 0. So what could be the small parameter? So the important observation is something that we have emphasized many times in previous chapters, is that this Ising system has a gap to excitations. That what I mean by that is the first excited state is a finite amount of finite energy above the ground state, even in the thermodynamic limit. So the first excited state is of course the single spin flip. You just go to a site and you flip the spin there. So there will be 4 broken links, 4 unsatisfied links. Those are indicated by the red color on the links. And you will see that the energy of this, the excitation energy of the state is 8J plus 2H. You're going from minus H to plus H in terms of the magnetic field. So the energy increases 2H. And each link, their energy is going from minus J to plus J. So there is an increase of energy of 2J, and there are 4 such links, and that's where you get this 8J. So what is a small parameter? This by itself is not a small parameter, but exponential negative of the excitation energy by T is a small parameter, because we are working this regime where J by T is very small, very large. T is much smaller than J, so J by T is very large, and therefore exponential of a negative large quantity is a very small number. So roughly speaking, e to the minus k, the coupling constant, is the small parameter in the problem. Okay, and this is sort of the thermal weight or the statistical factor associated with the flip of the single spin. So that is the small parameter in the problem. Okay, so what would be a way to organize our calculation so that we can get to our partition function of free energy in some controlled way in this small parameter? So since this is the small parameter associated with the single spin flip, we could try to organize our calculations by listing out configurations of spins with nf spins flipped. Okay, so remember, we are doing this calculation about the ground state and we are going to flip spins off the ground state. So this will be nf spin flip, means among the all n up spins, nf of them will be flipped down. Now you can easily convince yourself by some simple physical thinking that the statistical weight of any such configuration will be proportional to some power of this quantity, right? It will be some power of the small parameter. Okay, so there are some subtleties here. So what are the subtleties? Specifying the number of spins flips does not solely determine the energy of the configuration, as I will show you in the next slides. For a given NF, there are different types of configurations and different types of excitations, as you will see. Okay. So there is another issue. If you tell me a single spin flip and a certain type of excitation, you will see that there are various different ways in which those excitations can be realized. For example, the single spin flip can be realized in n different ways, where you can flip the spin at n different sites. So there is a degeneracy associated with each of these excited states. Okay. So this is the problem we have to deal with. So let's start with something that we know well. So suppose I take NF equal to 1, then there is a single spin flip. The energy we have already seen, and the degeneracy of this state is n because you can flip the spin in n places. So the NF equal to 1, the set of states associated with this, there are n distinct configurations with NF equal to 1. So the statistical weight depends on this, e to the minus 4k times plus 2h, and vanishes as t goes to 0, as we saw. And this statistical weight, what we are going to do is, you will see it's useful to introduce a picture for denoting this. So you see what I'm going to do here. I have this spin flipped here, and there are 4 links associated with it which have gone to the excited state. And what I can do is I can sort of take this site and sort of pretend that that is like a spin flip. So what I'm going to do is I'm going to introduce this diagrammatic notation. So there is a site in which a spin has been flipped, and there is a little square to say that, you know, those 4 links are excited. So each of these lines indicate that these things have been excited. So that gives me this 4 e to the minus 4 times 2k plus h tilde. So that's the picture for this, and its degeneracy is n. Okay, let me proceed to NF equal to 2. So here I have to flip 2 spins in any configuration. In the configuration I will have 2 spins. Now you will see there are 2 types of excitations where NF equal to 2, and those excitations have those configurations have different energies. Okay, so let's consider the first type of excitation. I'll call this the A type. Here the flip spins are adjacent to each other in the sense that they share a link. Now you will realize that if they share a link, both of these spins are down now. So this particular link is still in its lowest energy state. So the energy will be minus j. And since I have flipped this spin, you will see that there are 3 excited links. So they are indicated by red lines. And on this side as well, there are 3 excited links. Okay, so this is one kind of excitation. So basically it has 6 links that are excited. But I can also realize the 2 spin flip excitations by exciting spins on sites that are not adjacent to each other, as I have shown here. So here what will happen, each spin will increase the energy of 4 links, and therefore the energy will be larger than in this case. You can simply count that the number of frustrated links here is 6, whereas the number of excited links on this side is 8. Okay. So the first type of excitation is the NF equal to 2 excitation. The flip spins are on these sites, and the energy of this 2A state is 12J plus 4H, right? That's easy to see. And what I'm going to do is I'm going to indicate the statistical weight of this e to the minus 12K plus 4H tilde by this picture. So you can see that I'm now explicitly indicating that these 2 sites are nearby. I mean, they're adjacent to each other. And so I show that by not connecting this, link. And the idea there is that this link is not frustrated or it's not excited. Okay. So the degeneracy of this state is 2n. How do you see 2n? So you see, if you think of this as a square with this, let's say that you're going to think of this site here, the center of this as being located here. You see that this box can be put this way, or I could also have a adjacent spin on that side. So in another way of speaking, if I think of links emanating from a site, you can put one excitation along the X link or Y link, and there are n sites. Therefore, I can put X and Y independently on each of these n sites, and that's what gives me 2n. So it gives me an excitation, a probability of statistical weight of this, and a degeneracy of 2n. Remember, the degeneracy is now different from what we found for the single spin flip. Okay, but note that it's proportional to n. Okay. Let's look at the other case where the excitations are not adjacent. So now you see, the picture we will show is that there is an excitation of a single spin, and there is another excitation of a single spin which is not adjacent. So we put 2 dots, 2 separate boxes, to say that there are 2 distinct places where non-adjacent places where spins have been flipped. And the statistical weight of this is simply the product of these 2 statistical weights, which is consistent with our picture. So you will see that this number is simply the square of the term with one of these. Now comes an interesting observation. You can find what is the degeneracy of this. And you will find that is n times n minus 5 by 2. How do you see that? That's actually fairly straightforward. You put the first one. You can do that in n ways. Now once you put this, you remove the possible 5 places from which the second spin can be flipped. What are the 5 places? The same spin where you remove the same site where you flip the spin. And then of course the adjacent sites, 1, 2, 3 and 4. So now I have only n minus 5 sites available for me to place my second spin. And of course these two are not labeled, they are indistinguishable, so you have to divide it by 2. That's where this 2 comes from. Okay, so you see now something very interesting. You see that these kind of 2 spin flip process with adjacent, their degeneracy is proportional to n. Whereas the ones that are separated, that are not adjacent, their degeneracy is proportional to square of n. Okay. Okay, so we have done 1 and 2, so naturally we'll do 3. Okay, so now if you go to the NF equal to 3 excitations, you will now see that the number of types of excitation starts to grow. So for example, you can have 3 adjacent spins that are flipped. So in the configuration type A, all 3 of them are on a line. You can have 3 adjacent spins which are not on a line. So it's in this sort of L-shaped motif. So these are the only possibilities for realizing adjacent spins. Now you can have non-adjacent spins. So here what you can realize is, you can realize something where two of them are adjacent and one is away, or all three are away from each other and none of them are adjacent to each other. Okay, it will take a little bit of thought and work to do the full exercise of what I'm going to say. I'll just walk you through it quickly. So if you look at this 3A configuration, its energy turns out to be this, and the statistical weight can be expressed by this kind of a diagram, which clearly by now should be very obvious to you that it's telling you that there are 3 spins that are on a line. And if you just think about this for a moment, you will realize that the degeneracy of this is 2n, simply because you can again put this motif along the x-axis or y-axis starting from the leftmost point at any site, and that just gives you the degeneracy is 2n. If I go to the next type of excitation, it turns out to have the same energy as this. That's because the number of broken or the excited links are the same as what you have in the straight case. The difference here though is the degeneracy. So, okay, so this is a small error here. It should be actually a different kind of picture. I will show you the picture in the next slide. Let me just quickly show you what that picture will be. That picture will be something like this. Okay, all right. So this is an L-shaped picture, and the statistical weight of that is, it's the same statistical weight of this, but it will be 4, the degeneracy will be 4n. 4n, because you see this L-shaped motif at a site can be put in 4 different ways. It's like the 4 different possible orientations. And you can put this at any of the n sites, and so you will get a degeneracy of 4n. Okay, now if you look at the next term here, you will see the next kind of configuration. You will see that that comes as a product of a single spin flip, isolated single spin flip, and a product of and a picture that consists of 2 adjacent flipped spins, and you can see that's the statistical weight of it. Now you see again a very interesting phenomenon. You will see that the degeneracy of this again goes as n square. Okay. Now if you go to the next term, it's quite interesting and very it's a somewhat maybe somewhat challenging at the first shot to derive all this, but the idea is that you have 3 spins which are not adjacent to each other, and the probability of that will be simply cube of the terms that we have put down on the previous slide, and you will see that the degeneracy is this, and again very interestingly it scales as n cubed. So these terms, they scale as n, this one scales as n square, and this one scales as n cubed. Okay, so I'm not going to do n equal to 4 because we have only a finite time in this course and there are many natural numbers, so we'll stop there, and let's try to make a set of observations based on our study so far. So the first observation is that the energies of the configurations are not simply related to NF. The diagrams for statistical factors fall into 2 types. What are the types of diagrams? So you see, these are the set of diagrams which we call as connected diagrams. Connected means that there is only one motif in this. In any one of these diagrams, there is only one motif, and all the spins that are flipped, they will be adjacent to each other. So you can quote unquote reach any site from any other site in the set of flipped spins by taking single steps. You don't have to leave it's like a single domain sort of thing. Okay, so that's the idea. Then there are what are called as disconnected diagrams. So these are examples of disconnected diagrams. Right? The important thing to notice is that the disconnected diagram at any NF value will be products of connected diagrams of lower NF, of smaller NFs. For example, if you look at this disconnected diagram at NF equal to 3, it is a product of an NF equal to 1 and an NF equal to 2 connected diagrams. But note that the degeneracy will scaled differently. You have to work out the degeneracy more carefully. Okay. And now comes the most important observation, is that if you look at any connected diagram, its degeneracy will be proportional to n, always proportional to n, number of sides. Okay. And the degeneracy of any disconnected diagram will be proportional to n to the power number of connected pieces. So, for example, this diagram has two connected pieces. Therefore, its degeneracy will scale as n square. The leading term in the degeneracy will scale as n square. It can have subleading powers of n, that's okay. Okay. Now, if you look at this term, it has also two pieces, and therefore it will scale as n square, although it's an nf equal to 3 diagram. Now, if you go to this one, it's an nf equal to 3 diagram, but it's made of 3 connected pieces of nf equal to 1, therefore it scales as n cubed. Okay. So, this is what we find. These are the observations that we have made. If I put all this in a table, this is what it looks like. So, this is the configuration that we have discussed. This is the type, this is the energy, and this is the degeneracy. So, if you want to actually do a calculation, this might be a very nice way to tabulate things, and then you can mechanically perform calculations by just looking up the table. Okay, all this is very good, but where is this taking us? So, we have to find some physical answer which is by which we can understand the state about t equal to 0, and so we have to go to the partition function with all this. Okay. So, now here is my statement. Okay. So, what I am now going to do is, I am going to sum over the configurations of the excited states. So, I am going to compute this z that I had defined. Remember, now I am working with the energy relative to the ground state. So, that is why this E is here. So, the ground state configuration, the energy will be 0, and that gives me 1. So, that is the partition function of the ground state, if you wish. Then, when I go to the next term, that will give me what is the next term that I should get? I should get the single spin flip excitations. Those are the first excited states, and there are n of them, and they have the statistical weight given by this. And this is the 2 spin flips and so on, and I take all the terms that I have developed in the previous slide, multiply them by the degeneracy and multiply them by the statistical weight, and just go on. So, now remember, any blue box like thing is a small parameter. So, if you just keep this n as some fixed number, these are all small parameters. So, I can club all the small parameters and think of the whole thing as some kind of small parameter, which we will call x. So, you might wonder, all this looks like a bit of algebra, and where is all this going? So, of course, if I look at the partition function, it is difficult to see the physics. So, I need to go to the free energy. Okay. So, now remember, we have to add back the ground state energy, because we had calculated the partition function relative to the ground state, and therefore, F will be the ground state energy minus T log Z, this quantity. Okay. So, I have to take log of this. So, I observe that log of 1 plus x, which we have learnt in high school, goes like x minus x square by 2 plus x cube by 3, and so on. So, suppose you are very naive and you did not bother to think deeply about this, you will say, okay, all these are small numbers, so I am just going to stop at x. So, I will just say log of 1 plus x is x, and I will just keep this as the free energy. So, what will you find? You will find, suppose you make this approximation, you will find that the free energy is this, because I simply substitute x. So, just pause the video for a moment and figure out why this is not a very nice result. So, you will actually see this is a very scary result, because the free energy is not correctly extensive. You see, the ground state energy is proportional to n. These terms are proportional to n, but there is a term which is proportional to n square. So, it looks like the energy is proportional to the system size square, which does not make any sense. So we have immediately run into a problem by doing this sort of naive approximation of log of 1 plus x equal to x. So what's the catch? How do we get out of this problem? Okay. So what we have to do is we have to go to the next order. Okay. So I have to remember that this term is x minus x square by 2 and so on. I'm just going to keep terms of certain order so that I'll extract the terms of certain power in my small parameter correctly. So what I now do is I notice that I can expand this, and so this is the linear term, that's x, and the x square by 2 is this term. Now watch what happens. Okay, this is a remarkably beautiful result. When I square this object, you see this is a connected diagram of single spin flips. So when I square this, I will get a term which is n times this quantity, this statistical weight, 1/2 of that, the whole square. That term precisely cancels the n square power in this term. Okay. So when you see what is happening, higher powers of lower NF connected diagrams will kill the higher degeneracies, higher power n degeneracies of disconnected diagrams that we have found in our expansion. Okay, so this is a very, very important result, and it's actually quite general, and it goes, I'm slightly I'm taking a bit of liberty here to say that this is an example of linked cluster theorem. So if you have done any field theory, you know that there is something called linked cluster theorem. So this is morally quite similar to that, right? So you see that the connected diagrams are finally what contribute to the free energy. Connected diagrams and their powers. So you can see that this will give me connected diagrams. You will get power. So that's small parameter. So this box is a small parameter. The free energy is linear in the box, and I'll just put this terms, exactly calculated terms here. So it's linear in this box, and then there is a quadratic term in this box. So it's some e to the minus 8k, e to the minus 16k, and so on. But everything becomes correctly proportional to n, and the way the linear proportionality to n is obtained in the coefficient of any diagram that contributes to the free energy is by cancelling of the higher powers of n by higher powers of connected diagrams of lower order. Okay. So maybe that was a mouthful, but hopefully you can just revise this a little bit and figure out what I'm trying to say there. Okay, so I have now extracted the free energy. Now I know exactly what these pictures mean, and I can put them back into the equation, and I can find the free energy in this fashion. So I've got a free energy exact to some order of this, so that is what we have achieved. So all other terms in the free energy are some smaller powers of this, and you see this is by n. So these are literally all, they are. You can see that there is no n etc. surviving, and so we have got a free energy per density and so on. So if we truncate here, we know that we are doing pretty well because all other higher terms are really small. Okay, so if I stop here and simply obtain the magnetization, I will get m equal to 1 minus 2 times minus e to the minus 8j by t, which shouldn't be unfamiliar to you because this is what we calculated using some simple counting arguments. Mind you, in the previous lecture, there was a factor of 2 error here, which has been fixed in the notes. Okay, so what you could do now is you could pause the video and use these expressions and explore what does the magnetic susceptibility do at low temperatures, what does a specific heat do, and so on. So what are we learning from this exercise? We are learning about the properties of the ferromagnet. You can see if you go deeply into the ferromagnetic phase near t equal to 0, you are fully into the ferromagnetic regime, as we have seen, and we are finding like how is the susceptibility of the system, what is the specific heat, and so on. So we are finding the properties of the ferromagnetic fields. Okay, so that is where we'll stop in this lecture, and before I conclude, let me summarize. So series expansions are a very general tool that is used in theoretical physics for studying problems for which we know some solution for some coupling constant exactly, and then we expand about that solution and try to find some physics of the regimes near that exact solution. For the Ising model, the thermal excitation probability of a single spin flip is a small parameter, and so you can use that to expand the partition function and free energy. And terms can be organized as diagrams. Diagrams can be connected or disconnected, and there is a nice cancellation that shows up in a very nice way, so that the wrongly extensive terms in the free energy are cancelled out. And we have done some simple calculations to make sure that the calculations that we have done so far actually match with our previous calculations and our physical intuition. So what shall we do next? We will go to the high temperature expansion, where we'll work at infinite temperature or J equal to 0, whichever way you wish to think about it. So we have a bunch of isolated spins, and we will work to find out what is the physics around that point. We will then go on to take another look at duality, and I'm sure you will be very eager to know what the connection of the series expansions and duality is, and I'm sure you will not miss the next lecture. So I'll see you then. Thank you.